Now we have to substitute this expression here in this equation here. So now let me do it. The second derivative, it is very straightforward to calculate because we have to take the derivative of Cn prime times eta to the power n prime plus L plus 1, right? And so we can factor out this coefficient, and we can also divide by that coefficient, so that's just a constant. We can get rid of that when we substitute this expression in that equation there. So what we are really interested in analyzing is just this power of eta to the power n prime plus L plus 1. So if we take the second derivative of this term here, this will just be equal to n prime plus L plus 1 times L prime plus L n prime times eta to the power L plus n prime minus 1, because we have to subtract 2 from 1 here. And this is the second derivative, and then we have the first derivative, d of eta n prime plus L plus 1 with respect to eta, and this is just n prime plus L plus 1 times eta to the power n prime plus L, right? Yes. And now you have to remember that eta is a very, very large quantity, okay? So this term here will be negligible with respect to this one, because this term is greater than that term, is much greater, because this term here can also be written as eta to the power L plus n prime divided by eta, right? So when eta is large, this quantity will make that one very small. I mean, it will make it smaller with respect to this one here. So we can neglect this term with respect to this one. Of course, this term here can be very large, but compared to this one, it will still be small. Okay, so that's what I'm saying. But before dropping the term, let me rewrite it here. So let me rewrite all the terms. So I have n prime plus L plus 1 times L plus n prime times eta to the power L plus n prime minus 1. And then I have minus the derivative of q with respect to eta, and that will give me minus this term here. So minus n prime plus L plus 1 eta to the power n prime plus L. And then I will have minus from here, minus lambda over eta times q. So I have minus lambda, and then I can rewrite it like this, eta to the power n prime plus L, and then I have plus 1 minus 1. Okay, so I will cancel these two terms here. This minus 1 is present there because I had to divide by eta, if you recall. So I can put this eta in the numerator, and I will put a minus 1 here. But I also have a plus 1 because I have to substitute this expression, okay, into the differential equation. So here I can get rid of this, and then I have minus. Actually, it's a plus because I have, it's a minus. It's a minus plus, so it's minus L times L plus 1 divided by eta squared. So I have minus L times L plus 1 times eta to the power L plus n prime plus 1 minus 2. So I have n prime minus 1 here, and this should be set equal to 0. But we can still make some some more consideration here. As I was telling you some minutes ago, I told you that this term, the term that multiplies this coefficient, this coefficient that multiplies this term here, and then I also have this term here, they are negligible with respect to the term that multiplies eta to the power m prime plus L, and also this term here. So we can neglect these two terms and only consider for very large values of eta these terms here. So you have minus n prime plus L plus 1, and then I have minus lambda, and then this multiplies eta to the power L plus n prime, and this should be set equal to 0. From here, we derive that this coefficient that multiplies eta to the power L plus n prime should be equal to 0. Therefore, we get that minus lambda should be equal to n prime plus L plus 1. Okay, where n prime can be equal to 0, 1, 2, 3, and so on and so forth. Okay, so this means that now we can call we can call this parameter this is an integer, right? Because angular momentum is discrete, and we didn't show that here, but it can be derived from the other equation, the other differential equation, the differential equation for the eigenvalue equation. So it is the eigenvalue equation for L squared, the operator L squared, the angular momentum squared. And it is possible to show that this quantity here should be an integer. But now if we call this integer n, from here we get that n starts at L plus 1, and then we get L plus 2, and so on and so forth. So this means that n is greater than or equal to L plus 1, or if you want, L is less than or equal to n minus 1. Okay, so you can also write it like this. And now from here, we can find the discrete spectrum of the energy, because we know that lambda, or minus lambda, is equal to z e squared divided by h bar square root of minus mu over 2e. And when I wrote down this expression, and the first time this minus sign was not present. Actually, there should be a minus sign here, and I didn't write it down, but I put it in the notes. So this minus sign can also be put here, of course, and this quantity is equal to n. It is that integer n that starts from L plus 1 and then L plus 2 and so on and so forth. Okay? And from here, you can see that this energy, I mean, the only thing that can change inside this expression is the energy. So the energy can depend on the subscript n. So it's E sub n. That's a constant that can depend on this integer n. The only quantity here that can be dependent upon this integer. And now if you square both sides of this equation, you get that you want to find the expression for the energy, right, from there. So you can write that n squared is equal to minus z squared e to the power 4 divided by h bar squared times mu divided by 2 e sub n. And from here, you get that e sub n is equal to minus z squared e to the power 4 times mu divided by 2 h bar squared times 1 over n squared. Okay, and this is the important expression for the energy. You can see that it is discretized, it is discrete, because there is this integer present, and n is an integer that in principle can start from L plus 1 and then L plus 2, L plus 3, and so on and so forth. Okay, so you can see that the larger this integer, the more, let's say, the closer to 0 the energy. So the energy in here is negative. So it means that when n is very large, the energy will become the spectral lines will become more dense, very close to n equal to the values n equal to 0. Okay, so it will be almost continuous when this integer will be very large for I energies, because when n is very large, the energy will become higher, because remember that this quantity here is negative. So it means that the kinetic energy of the electron will become much higher, and the hydrogen atom, will become unstable when we have n very large. Now here I'm just drawing some spectral lines, and you can I mean, this is just for the sake of visualization, in order to visualize the energy levels. So this is for example associated with a low value for n, whereas here we have very high values for n. Now, this expression here was already derived, I mean, it had already been derived by Bohr. It is also known as Bohr's model. In order to derive it, Bohr had to make use of ad hoc hypothesis. So he derived this from empirical evidence, whereas we managed to derive it here from the Schrödinger equation, which underlies an incredibly much more solid theory.